Hello again, Calculus 1. Welcome to episode 7 of Recitation during this beautiful summer 2020. Today we are going to be talking about how differentiation rules. Like, differentiation is awesome. Like, I don't just mean like, oh yeah, the rules of differentiate. No, I mean like differentiation rules. I mean, we are also going to be talking about, the rules of differentiation. Don't get me wrong, but that was the pun in the title. Please appreciate it. We are also, on top of differentiation rules, going to be talking about the derivative, as a function. So in 3.1, we looked at the derivative at a specific value of x. And in 3.2, we move into looking at the derivative as more of a function rather than a specific value. It's a function for which we can plug in any value of x and get an output. Any value of x within the domain of the function for which the function is differentiable. So let's jump into it. You can see I've already written out the first problem here. There are 8 of them which I want to do today, which we'll see how the timing goes. I actually had a lot more picked out. There are so many great problems in these 2 sections, but I did have to narrow it down a little bit. So we'll see how the time goes. The main reason that I had already written out the first problem is because I actually made a silly the first time I went through doing it. So I had to stop recording and restart, but I didn't feel like erasing the problem itself. So here we are going to be finding a particular derivative. The function is y equals 9 over the square root of x minus 6. We are asked to find dy dx, in particular the derivative of y with respect to x. That respect to part isn't super important here because there's clearly only one variable here on the right side. However, there are other situations in which that will be very important, and I think that we're going to talk about that in at least one of the problems today. Then we're going to find the equation of the tangent line at the point 7, 9. So that's what we're in for. The interesting thing about these sections together, 3.2 and 3.3, is that in 3.3, you learn a lot of tricks which would make the problems in 3.2 a good bit easier. So what I'm going to do, and for the sake of this video, I'm going to do the 3.2 problems, which I think is really just one actually. I'm going to do this first problem using the definition of the derivative rather than using our fancy tricks. And then the remaining problems from section 3.3 I will do to practice using our new handy-dandy tricks. But it's important that you know how to use the definition of the derivative to find derivatives. So that's what we're going to do here in problem 6, and I encourage you to make sure that you know how to do that. Now, if I was doing this first problem with tricks, I decided I'd go ahead and tell you what I would think, how I would go about it here. What I would do if I wanted to find this derivative, well, first I would rewrite 9 over the square root of x minus 6 as 9 times x minus 6 to the negative 1/2 power, right? Root x minus 6, 1 over root x minus 6, I should say, is just x minus 6 to the negative 1/2. And doing that, the great thing about doing that is that then I get to use the power rule for derivatives. We're also going to have to use the chain rule if we were doing this all the way. But by using the power rule, that simplifies the problem a good bit rather than trying to use the quotient rule. I personally prefer power rule to quotient rule, and I think most people would say that they agree. So when I say the power rule, what I mean is this rule down here that the derivative of x to the n, is just n times x to the n minus 1 for any real number n. This works whether n is an integer, whether it's a fraction here, a negative fraction, it doesn't matter. So that's the great thing about the power rule. And as I hope you will see both throughout this video and throughout the remainder of your time in this course, the power rule is very much our friend. But in this problem, we are not going to be using the power rule. So let's go ahead and write out the definition which we are going to use. So we're going to look at the limit as h approaches 0 of this fraction. Now you'll notice one difference between this and what we did in section 3.1 is that rather than plugging in a specific value of x here, we're just going to plug in the variable x. We'll then do some simplification, which allows us to write this as a function of x rather than just a specific value. So that's the benefit of using the variable here, is that it allows us to compute a lot of derivatives really quickly, essentially. Rather than just finding the derivative at one point, we can find a general formula for the derivative at any point on the graph. So let's go ahead and plug those things in. Okay, whenever I plug in x plus h, that gives me 9 over root x plus h minus 6, not x plus h minus 6. And whenever I plug in just x, I get 9 over root x minus 6. All of that is going to be over h. Oh boy, that numerator looks so fun. So this numerator looks kind of like a pain in the butt to deal with these square roots in the denominators and everything. How am I going to simplify that? Good Lord. So what I'm going to do is I'm going to multiply. Basically what I'm going to do is I'm going to get a common denominator here. The way that I'm going to do that, I'm going to multiply that fraction on the left by root x minus 6 over root x minus 6. Okay, so notice that this root x minus 6, that's just the denominator of this right-hand fraction. And similarly, I'm going to multiply this right-hand fraction by the denominator of the other fraction, which is root x plus h minus 6. Okay, so notice where these values are coming from. What I mean, I've written it off to the side here because there's no space. What I mean is I'm going to multiply the one in green, parentheses, by the green fraction, and the one in red by the red fraction. Notice that they're both just fancy ways of writing 1. But the way that the nice thing about it is that we are going to get, okay, so let me see. That's going to give me 9 root x minus 6 over root x minus 6 times root x plus h minus 6 minus, and now 9 times root x plus h minus 6 over, same denominator now, root x minus 6, root x plus h minus 6. All of this over h. Okay, so still not super clean yet, I'll be the first to admit, but I think we're on the right track. So what I'm going to do now is let me rewrite that numerator. Let me combine those into one fraction. So now it's going to be 9 times root x minus 6 minus root x plus h minus 6. And then in my denominator, I've got this common denominator, x minus 6, root x plus h minus 6. And when I say the denominator, really what I mean is the denominator of the numerator, because we still have this h down in the denominator, the main denominator, I don't know. But I can bring the denominator of my numerator down into the actual denominator. 9 root x minus 6 minus root x plus h minus 6. I factored out a 9 above. I didn't verbally say that, but as you can see, these both have a 9 in front, so I just factored that out. Okay, I hope I didn't lose anybody there. I'm sorry if I did. And now in the denominator, I've got h times root x minus 6 times root x plus h minus 6. Okay. Oh boy. Well, let me see. This is still a problem because if I plug in h equals 0, I'm still going to get a 0 in the denominator, which is no bueno. So this is still a problem. But what I can do, in fact, I'm going to get what on earth? I'm going to get a 0 in the numerator and denominator if I plug in h equals 0. But what I see in the numerator is I've got root of something minus root of something else, right? I'm just writing a and b here. The point is that it's square root of something minus square root of something else. And what we've done before when we've had something kind of like that is we've done this little trick. I need to stop clicking the screen. We've done this little trick where we multiply by the conjugate, right? So in this case, that would look like root A plus B over root A plus B, right? Where A and B are these things here. So that's what we're gonna do. So let me mark that, multiply by conjugate of, so multiply by the conjugate, so that gives me, okay, limit h goes to 0 in my numerator, so I've got 9 root x minus 6 minus root x plus h minus 6 over h root x minus 6 root x plus h minus 6 times, so let's go ahead and write out that conjugate. That's going to be root x minus 6 plus root x plus h minus 6. Okay, so everything under the radical stays the same. I'm only changing the sign in the middle of those two radicals. Okay, so let's keep on going. In the numerator, this is where the magic is going to happen because this is where conjugates do their thing. I'm going to be left with 9 times x minus 6, and then minus, parentheses, the square of the other one, x plus h minus 6. Okay, all of that over, okay, this denominator is going to be a bit of a pain. Well, whenever I multiply root x minus 6 times root x minus 6, the root is going to cancel, and this is just going to be h times x minus 6 times root x plus h minus 6. Okay, right, the radicals there canceled out. And similarly, now I'm going to do plus, and the root x plus h minus 6 times root x plus h minus 6 is going to cancel. The radicals are going to cancel, rather. So that's going to be plus h times now root x minus 6, x plus h minus 6. Okay. Well, now this numerator, let's see what's happening there. I've got x minus x, and I've got minus 6 minus minus 6, so minus 6 plus 6. So my numerator now is just negative 9h. And in my denominator, both of my factors have h's, so I can pull those guys out. And I'm left with h times x minus 6 root x plus h minus 6 plus root x minus 6 times x plus h minus 6. There we go. Okay, it looks kind of ugly, but it's actually not so bad, especially because now we get to cancel again. We've got h in the numerator, h in the denominator. Limit as x goes to 0, and I've got negative 9 on top, and on bottom, see, I've got, there should be a limit as h goes to 0. I've miswrote it 2 times now. There we go. H. So that's negative 9 over, okay, let's see, so that's x minus 6, x plus h minus 6 square root of that, plus root x minus 6, x plus h minus 6. Well, now, if I plug in h equals 0, plug in h equals 0, so we're going to go ahead and take that limit now. And then I'm going to get negative 9 over, let me see, so that's x minus 6, and then that just becomes a root x minus 6. Right, if h is 0, that's just square root of x minus 6, plus root x minus 6, x minus 6. And now, let me see here, well, x minus 6 times root x minus 6, that's just, how do I want to write this? That is x minus 6 to the 3/2. And I've got two of them because I've got one on the left here and I'm adding it to a second one on the right. So I think that our final answer now is going to be negative 9 over 2 times x minus 6 to the 3/2. And I believe that gives us our solution. One of the great things about learning these new tricks is that we can use them to check our answer on these guys. So let me see. Yeah, that works. So this is a good time to demonstrate this other way of doing it real quick. So let's go ahead and do that just to check it. So we had y equals 9 times x minus 6 to the minus 1/2. So what I'm going to do, so then dy dx, bring the negative 1/2 out front. So that's going to give me minus 1/2 times, well, this 9 is just a constant. So it can, in fact, let me pull that 9 all the way out front. So the 9 is just a constant. So we can just pull him out front and worry about him later. To deal with the rest of it, I'm going to multiply by negative 1/2. Okay, bring that negative 1/2 down front. Then I'm going to leave the inside alone, so that's still x minus 6. And now the exponent, I'm going to lower by 1. It's minus 1/2 minus 1. We'll go ahead and figure that out in a second. Now I need to multiply by the derivative of x minus 6. Right? That's the chain rule, so that's where this comes in. This right here, that's chain rule. And let me see, so this comes out to minus 9 over 2 from my constants out front. This becomes x minus 6 to the negative 3/2. So x minus 6 to the minus 3/2. And the derivative of x minus 6, well, the derivative of x is just 1. Okay, we can use power rule for that. So that's just a 1. And the derivative of the minus 6, remember, we can just add the derivative of x plus the derivative of minus 6. And the derivative of minus 6 is 0 because it's a constant. And so this just becomes times 1. And this now, negative 9/2. And then I can rewrite x minus 6 to the minus 3/2 as over x minus 6 to the 3/2. And that is exactly what we got. Okay, very good, very good. If I went a little too quickly for you in this little derivative computation at the end, we'll do a lot more derivative computations over the next few minutes, and I'll be sure to take my time on those. I didn't want to spend a ton of time on this one simply because that we had already done the problem, and I want to make sure we have time to move on. Okay, so the second one is a pictorial one, which I don't normally do in these videos, partly because I'm not good at drawing pictures, so sometimes it can be confusing. But I think here, this is a cute little problem, and so I wanted to show it. The function, graphs on the right, because there's a very important idea at play here on the right. So the function, which I guess I'll draw it on the right because that's what the instructions on my computer say. The function looks something kind of like this. It doesn't have numbers or anything like that. I'm not just being lazy. It looks just something like that. So the point, which I want to emphasize here, and we'll get there in just a second, but the point that I want to emphasize here is that the derivative at x is the slope of the curve at x. Slope of the curve at x. Okay, this is really the key idea which this problem aims to get at. So let's make another picture down here where we're going to draw our derivative. So we'll call this one f of x, and down here we're going to draw f prime of x. I'll invert it. I'll use the opposite colors for this one. It's a terrible x-axis. That's better, but still not great. Okay, so if we look at this first part of the graph, let me highlight it. If we look at this first part, I actually have a highlighter. From like this region here, it will go up until like there. We can see that the slope is negative. Okay, so slope is negative because the graph is decreasing, right? Things are going down. So if I'm graphing the slope on over here, that means that I need to be negative at the start. Now, at this point here-ish, right around here, I would say, we can see that the slope is 0 because we're not getting bigger and we're not getting smaller at that point, right? Like we're not going up, we're not going down at that point. And then, after that, we start to, let's use green, we start to get positive, right? So here, the slope is positive. And what we notice is that the slope is pretty much increasing the entire way. Like we can see that, well actually, do I want to say that? Let's not say that right now. So there are a few choices on the computer screen in front of me for this problem. But here's what I notice. So at this point here-ish, we'll call it here. Actually, do it in red. Right here, I know that this point is on my graph because at this particular x value, the slope is 0. Right, so in this case, remember the x, so this is like the x-axis, and this is like the f prime axis. F prime. Okay. So f prime at this particular x value where the red dot is 0, so that's why we're on the x-axis there. Now to the left of that, I see that I am below the x-axis. Okay, so it doesn't necessarily, so to the left of that, we're below the x-axis, and to the right of that, we are above the x-axis. And so we can see, in this case actually, it does turn out that our derivative function looks like a line. However, the main pieces of information which you would use to solve this problem, well, on the computer screen, there are 4 choices, and this is the only choice for which, the picture that looks like this, for which we are below the x-axis here, right? There are 3 key points here. We are below the x-axis here because the slope is negative, okay, because f prime is negative. We are then at 0 here because the slope is 0 at that point on f of x. And then we are above the x-axis after that because the slope is positive. Those are the key points. And those pieces of information are what help you decide upon the appropriate graph in this case. Okay. To see that it was a line, you would need to do a bit more work involving second derivatives. But this right here gives you all the information that you need to solve the problem. Okay. The next problem that I want to do is problem 14. Problem 14 I put a star next to because I was really excited about it. Oh, and I see why I was really excited about it. Okay. Oh, I just realized, I apologize. In this first problem, I did not go back and find the tangent line at this particular point. Frankly, I figured at that point, so to find the slope of at that point, you would just plug in x equals 7. So just draw a quick note to find slope at, what's my point? My point was 7, 9. You just plug x equals 7 into this formula that we found, and then you would use point slope form to find the tangent line. You have a slope then, and you have a point. Okay, sorry. Back to where we were, and where we were was problem 14, which I was so hype about. So here it says find the derivative of the function. So the function is z equals 2 minus t times 1 plus t squared to the negative first power. The reason I was excited about this is that there are two ways of doing it. The first way, we'll go ahead and use product rule. Product rule is probably the most natural choice here because I look at it and I see I've got a product of two things. Okay, so let's review product rule very quickly. So product rule says that if I have f times g, so if I want the derivative of f times g, where say this first function 2 minus t is f, and the second function is g, to do that I do f times g prime plus g times f prime. Okay? It doesn't matter which order you do it in. The great thing about addition is that it's commutative, and so we can do it in either order. Right? If I want to do gf prime first, that's fine. It doesn't matter. So let's go ahead and do it here. So the derivative of, all right, so f is just 2 minus t. So let me draw dz dt equals, okay, f is 2 minus t. Notice I'm writing dz dt because z is the name of our function here. 2 minus t, now I need to multiply by the derivative of g. Well, to do that, I'm going to use power rule. So I'm going to bring that negative 1 down front, multiply that by the inside, 1 plus t squared. Now I need to lower the exponent by 1. Okay, so negative 1, I'm going to lower that exponent by 1. Now I need to multiply by the derivative of the inside, and the derivative of 1 plus t squared is 2t. That again uses power rule. Okay. So the derivative of 1 is 0, and the derivative of t squared, well, I can just bring that 2 out front, and I get 2t, and I lower that exponent, I just get 1. So let me highlight the fact that I'm multiplying by 2t here. This is chain rule at work. Okay, and this first part here, well, that was power rule. Power rule. Okay, and let me actually highlight this as well. This part here is g prime, and this part here is just f. Okay, I'm going to go ahead and move to a new line real quick. Plus, now g, okay, so g was 1 plus t squared to the minus 1. And then the derivative of 2 minus t, well, that's just minus 1. Okay, minus 1, because the derivative of 2 minus t, well, the derivative of 2 is 0. So I have 0 plus the derivative of minus t, and the derivative of minus t is just minus 1. Okay, so this right here, this minus 1, this comes from, this is f prime here. and this 1 plus t to the minus 1, that is just g. Okay, so let's go ahead and multiply this out. We can simplify it a little bit. And that first part, okay. So I've got a 2 minus t times negative 1, so that's giving me a t times t minus 2. I'm going to move the 1 plus t squared to the denominator so that I can make that exponent positive, that minus 2 exponent. And then I've got a 2t still, and we can multiply this out. We'll go ahead and do that real quick. That gives me 2t squared minus 4t all over 1 plus t squared squared. Okay, so this is our derivative done using product rule. Now I again want to do this derivative. This time I want to use quotient rule. And you might say, but Bailey, I don't see a fraction anywhere here. Well, dear student, excellent observation. And what I can do is I can rewrite, so z, we are told, is 2 minus t times 1 plus t squared to the minus 1. And 1 plus t squared to the minus 1, well, that's the same as 2 minus t over 1 plus t squared. Okay, so now we get to use quotient rule. In quotient rule, I like it generally less than product rule. I think most people do because it's easier to get confused. This says that if I want the derivative of f over g, so f over g prime, well, that I have to check myself and make sure that I get it right every time. So that is going to be, what is it? Come on. Is it plus or minus? I always forget. So I know in my denominator I have g squared. In my numerator then, let me see, I introduce a negative where I take the derivative. Yeah, okay. In the numerator then, I'm going to have f prime g minus g prime f. Now, the way that I think about this, the way that I remember this, you can actually, and I'm not going to go through it in detail here, but notice that you can actually derive quotient rule from product rule. So notice that f over g is just f times g inverse. And then we can use product rule and chain rule to get this formula here. Okay, so I think about it the second way, honestly. That's how I remember the negative here, because whenever I think about it, I think, oh, whenever I take the derivative of g, I introduce a negative 1 because of power rule. But whatever makes sense to you, so long as you can remember, however you can remember this formula. Again, it's important that you remember which one goes before the minus sign, because the order does matter in this case. Okay, but let's go ahead and stop talking and start doing. Let's do it this way as well to demonstrate quotient rule. So again, in this case, let me just... So f is 2 minus t, and g in this case is 1 plus t squared. We're not worrying about the negative 1 anymore, because once we've moved this function to the denominator, it's not an issue. Okay? So let's go ahead and compute this derivative. So dz dt. Okay, so first I need the derivative of f. We did that before, and that is just minus 1. Remember, that is just because it's the same as the derivative of 2, which is 0 because it's a constant, plus the derivative of minus t, which is minus 1 by power rule. So that's minus 1 times g now. So g is 1 plus t squared. Okay, so this right here is f prime. This right here is g. minus g prime. Okay, so g prime is going to be, well, let me see, that's the derivative of 1 plus t squared. Well, the derivative of 1 is 0. It's a constant. And the derivative of t squared, that's going to be 2t by power rule. So that's 2t. And then I multiply it by f, which is 2 minus t. Okay, so here I have g prime. And here I have f. And in my denominator is g squared. And g is 1 plus t squared. 1 plus t squared squared. All right, let's go ahead and multiply things through. I might do this kind of quickly just to save time. Let me see. So minus 1 minus t squared minus 4t plus 2t squared all over 1 plus t squared squared. Let me see, and this is equal to, okay, minus t squared plus, so that's t squared minus 4t minus 1. Did I do something silly here? Oh, let me see. Minus 1 minus t squared. 2t squared minus 4t. Let me see. Minus 1 minus t squared minus 4t plus 2t squared. I just found a... So the problem, I just looked back at it for a second. The problem came in the first one. I was confused because our answers weren't matching up. And I'm just now seeing that in the first one, we totally neglected, poor little guy, we totally neglected to add him in, this plus 1 plus t squared to the minus 1 times negative 1. So if we do that, then everything works out nicely. I'm not going to go through that here in the interest of time. However, so if we go ahead and finish what we started down here, t squared minus 4t minus 1 over 1 plus t squared squared. This gives us our derivative. In fact, let me go ahead and double check what we did up here. Let me see what I would get. So let me go ahead and try and fix this real quick. So, okay, so I need to do this thing, but then I need to do minus 1 over 1 plus t squared. Okay, well, that's the same as 2t squared minus 4t minus 1 plus t squared all over 1 plus t squared squared. And yeah, that does give me exactly what we just got. Okay, t squared minus 4t minus 1 over 1 plus t squared squared. And that is exactly what we just got down here. Sorry about that. Oh my goodness. So that gives us problem 14. And I hope that my mistake right there just demonstrated to you, hey, it's really nice to be able to check our work and do things in two different ways. So learn from my mistakes and also the good things that I do, like doing things two different ways to check. Okay, next up, problem 17. And here we are going to find the derivative. And so the function here is y equals 9e to the minus x plus e to the 2x. So we've used chain rule earlier in this video, but I'm gonna do it more slowly and deliberately this time. So notice that e to the minus x, well, this is the composition of the function. So let's call it the composition of f composed with g of x where g of x equals negative x, and f of x equals e to the x. Okay, right? So let's see this real quick. So f composed with g fog of x equals, well, that's just f of g of x. So that's just f of negative x, and that's e to the negative x, which is exactly what I said. It's exactly what I claimed. Which means that the derivative of e to the minus x equals, so the derivative then is going to be, oh shoot, what am I trying to say? I lost my train of thought. So then the derivative of e to the minus x, so this is going to be, we're going to take f prime of x, and we're going to evaluate that at g of x, and then we're going to multiply that by g prime of x. Okay? So in this case, let me just make a note. So f prime of x is just e to the x. Okay, that's one of the very important derivatives which we've learned in this section. The derivative of e to the x is just e to the x. So f prime of g of x, well, that's f prime of negative x, and that is just e to the minus x. Okay? So all that we did was we plugged minus x in for x. And then g prime of x, let me go purple. G prime of x is the derivative of negative x, which is just negative 1 by the power rule. So this comes out to e to the minus x times minus 1, or minus e to the minus x. Okay, so if we go back to our original then, we have, let me go ahead and rewrite it. We had y equals 9e to the minus x plus e to the 2x. Okay. Well, derivative of y with respect to x, first of all, let's go ahead and break this up. I'm going to be very deliberate with all the rules here. So it's the derivative of y with respect to x of 9e to the minus x plus the derivative of e to the 2x. Well, I can bring the 9 out front because it's just a constant. So that's the 9 times the derivative of e to the negative x plus the derivative of e to the 2x. E to the 2x. Okay, so we just figured out that the derivative of e to the minus x is minus e to the minus x. So this is 9, or minus 9e to the minus x. Now, how about e to the 2x? What is that derivative going to be? Well, if we do the same thing, then we can say that e to the 2x is the function, how do I want to, so I don't want to introduce new functions. So e to the 2x, in the same manner, if we go back and look at what we did to compute the derivative of e to the negative x, if we just change negative x here to 2x, then everything else is going to work out exactly the same. And so we find out that the derivative of e to the 2x is 2e to the 2x. I encourage you, if that isn't clear to you, take some time and go through and compute e to the 2x, that derivative by yourself. I think that would be a good exercise, a good way to practice kind of the same ideas which we did here with e to the negative x, but use them in this other setting. Okay. Next problem is I want to do problem 20, but I'm only going to do part A. There are a few parts of this problem, and I think it's the kind of problem where the first time you look at it, you might be confused, but I think once you see one part of it, you will hopefully see how to start doing the others. So suppose u and v are functions of x, which are differentiable at x equals 0, and that. So these are going to be the key pieces of information here. U of 0 equals 2. U prime of 0 equals 4. V of 0 equals minus 2. And V prime of 0 equals 9. So then find the following derivatives. Here it'll just be one derivative because we're just going to do one part of it. The following derivative at x equals 0. And the derivative that they want us to find is, I'll write it, d dx of uv. So we're not actually told what the functions are. We're just given these few specific values. However, we do have enough information to find all of the derivatives that we need. And here's why. So I don't know what u and v are, but I do know from the product rule that this derivative is just u prime of 0, v of 0, plus u of 0 times v prime of 0. This right here, this is just the product rule. And even though I'm not told what the functions are, I'm given all the values that I need, right? So u prime, I don't know why there shouldn't be a d dx here. There we go. So u prime of 0, we're told is 4, so that's 4. V of 0 is negative 2. Plus u of 0, we're told is 2. And v prime of 0, we're told is 9. And so this just comes out to be 10. Okay, so really all that we need to do here, I think this problem looks really scary because like I said, we're not even told what the functions are. But actually, as long as you know your formulas and you know your rules, or you can look up your formulas and your rules, then you should be in pretty good shape because you have all the information which you need. So like I said, that's a 4-part problem, and I'm leaving most of the fun to you. Don't worry, I didn't spoil too much of it, but I figured I should at least kind of show you how to approach this problem in case that was a little bit scary for you. Okay. Now we are on to 23, where we are told to find the first and second derivatives. 2 derivatives. What? And second derivatives. Okay. So Oh, I should probably tell you what the functions are. So the function is R equals 1 over 2s minus 6 over 5s to the fourth. So this is a 5. And this is an s, the other one. Okay, so here I'm going to use a trick very similar to what I talked about in the very first problem of this video. I'm going to rewrite this as r equals 2s to the minus 1 minus 6 times 5, or actually let me write it this way, minus 6 over 5 times s to the minus 4. And actually, let me go back and rewrite this first one as 1/2 s to the minus 1. That looks better. That's good because now whenever I apply, because now what we're going to do, so to find the first derivative, we are going to apply the power rule. Okay, so that's all we're going to do here, really. I think there's actually going to be a little bit of chaining. No, actually there isn't. So the first derivative, 1/2, I've got this 1/2, which is just a constant, so it's just chilling here, times I've got a minus 1, right? I'm bringing this minus 1 down to use product rule. And then I've got a minus 6 over 5 times minus 4 s to the minus 5. And we can rewrite this a little bit. Let's go ahead and do that. So I have 1/2, so it's minus 1/2 s to the minus 2. And let me see, I've got minus a negative, so that's actually going to be a plus 24 over 5 s to the minus 5. 4 over 5 s to the minus 5. I don't like whenever authors use s as their variable because, well, for obvious reasons. So this is a 5 in the denominator, and this is a 5 in the exponent. So that's a 5, and that's a 5. The circled equals 5. That says circled equals 5, not 0 equals 5. Yeah. So I think this is a whole lot easier than trying to use quotient rule. I think just using the power rule here makes your life a whole lot easier. So I encourage you to do things that way and to use the power rule whenever you can. I think that is, generally speaking, probably the easiest derivatives to take are the ones involving power rule. So this is our first derivative. I will leave the second derivative to you. Again, I don't want to spoil too much of the fun, and also just in the interest of time, keeping this video at about an hour. Okay, but that's how we go about finding the first derivative. The second derivative, I think from here you should be in pretty good shape. So to find the second derivative, all that you do is take the derivative of the first derivative. So you want to do dr ds of minus 1/2 s to the minus 2 plus 24, or actually dds. dds, minus 1/2 s to the minus 2 plus 24 over 5 s to the minus 5. And then you'll be good. All right, we have two more that I would like to go ahead and knock out in this video. The first one is problem 27. So 27. Oh yes. Find all points on the graph of f of x equals 2x squared minus 3x with tangent lines parallel to the line y equals 9x plus 5. Okay. Well, let's take a brief second to review what it means for two lines to be parallel. So two lines, well, I shouldn't say what it means, but how to tell if two lines are parallel. Two lines are parallel if they have the same slope, but are not the same line. Have the same slope, but are not the same line. Okay, so here, the slope of y equals 9x plus 5, well, this is in slope-intercept form. So it's 9, we can see it's just this coefficient of the x. So this question is really asking, for what x is f prime of x equal to 9? That's really what this problem is asking whenever you get down to it. I guess the other caveat is that we have to make sure that for any x values we find, that the tangent line is not literally equal to 9x plus 5. But that's essentially what we need to do here. And to do that, what we need to do to figure out which of these x values this is true for, is we need to find f prime of x. Okay, so f prime of x, well, let's see. Okay, this isn't so bad. So this is just going to be a power rule. Okay, so 2x squared, we take the derivative of that, and we will get 4x. Okay, we're going to bring that 2 down front. Right, we're going to bring that 2 down. So then I have a 4x, and now my exponent is just a 1. So it's 4x. And then if I look at 3x, okay, well, again, that's just power rule, because if I bring the 1 down, right, there's an imaginary 1 here. Because if I bring that 1 down, multiply it by the 3, then I get 3x to the 0 power. X to the 0 power is just 1. So that's just 4x minus 3. Okay, so now we set 9 equals 4x minus 3. And we solve for x. So then 12 equals 4x, which means that x equals 3. Okay, so let me see. We want to find all points on the graph for which, okay. So we found the x coordinate. So now we just need to find the y coordinate. Well, y, it's just going to be what I get whenever I plug in x equals 3. So 2 times 3 squared minus 3 times 2. Okay, and this gives me y equals, okay, 3 squared is 9, that's 18, minus 6 is 12. So my point is 312. Now, I must check, is 312 on the line y equals 9x plus 5? Because if it is, then these two lines are not parallel, but they're actually the same line. So they're not parallel, they would be literally the same. Well, to see that, we just plug the value to check that. There are several ways of doing it. What I'm just going to do, is it true that 12 equals 9 times 3 plus 5? Question mark? No, silly, absolutely not. so the lines are parallel. Meaning that the solution then is going to be 312. Okay, so real quick, again, the slope of the tangent line is given by f prime of x. So we were really just looking for what x values satisfy f prime of x equals 9. And in this case, we were able to find that point. That point was 312. There could have been more, but in this case, there happened to not be. And that gave us our solution. We did have to check to make sure that it was not literally the same line as the one we were interested in, but thankfully it was not. Okay. The final problem for this video is problem 29. And there is one important point that I wanted to talk about with this one. Oh boy. This is a long problem. I'm not going to write out the details. Here's what you need to know. So we're going to be given the function r equals m squared times c over 2 minus m over 3. Okay, so we're given this function, and we are told to find dr dm. Okay, now this is important right here. This is the key that I wanted to talk about. Since it says dm, this means m is treated as a variable. So m is being treated here like x. And all other letters are constants. All other letters are treated as constants, Okay, so C, for example, C is a variable in this problem, right? Actually, it does say that C is a positive constant. But it looks like, so I guess C is a constant, but the point that I'm trying to make, it looks like C is another variable here, because it's a letter, and letters are usually variables. But the fact that it says find dr dm tells us that we treat C like it's a number. Okay, so you're going to treat C like it's, I don't know, like it's 3. Or 4, or whatever number you like. You're still going to write C, but the point is, like whenever we're doing chain rule or product rule or things like that, we're just treating it as a constant. Okay, so let's go ahead and do this. So what I'm going to do, there are different ways of doing it. You could use product rule from the get-go, but I think if I distribute this m squared, that'll actually make my life easier, because then I'll get c over 2 m squared minus m cubed over 3. And now to take the derivative of this, all that I need is power rule. Again, I'm sure you're sick of me. You're probably sitting at your computer saying, oh my God, say power rule one more time. I swear to God, Bailey. Power rule. But that really is the way to go whenever we can do it. That's, in my opinion, I think in most people's opinion, probably the simplest rule to use. So if I use power rule in this first one, we get c over 2 times 2 times m. Okay, the 2, this just comes from the exponent, the m squared. And then I lowered the exponent, so now I just have m. And then I really have a 1/3 out front here of the m cubed. So let me see. So then I have 1/3 times 3 times m squared. Again, just applying power rule. And hey, our fractions work out super nice. C over 2 times 2 is just c, so this is just cm. Minus 1/3 times 3 is just 1, so that's just minus m squared. And this is our derivative with respect to m. All right. Okay, well, I hope that you have found this video to be helpful. I'm sorry, I think I misspoke quite a few times. I'm quite tired as I am making this. I've been studying for my qualifying exams all day, which I need to pass in August to stay in the PhD program. So, we're doing a lot of studying. I hope that your exams went well. Please let me know how I can help you be successful in this course. Please send me problem requests. I haven't been getting many, which is fine. Don't send them if you don't have them. But I would love to get some. So please just let me know how I can help you. Sometimes I feel like I'm not being helpful without the request.